IBS is a system in which building components are made in factories, on-site or off-site, transported and then assembled into a structure with minimum work. The advantages are high-quality product, faster and more efficient, less work to do, increased site safety and also flexibility. We have taken PP1AM as our building precedent in this project. We did some amendments on the plan to understand further how different IBS components work. We have researched companies that use IBS system and applied it on the components shown above, such as foundation, columns, beam, walls, slabs, and staircase. The schedules shown on screen are the different component schedule used in our building, using different sizes, heights, and also lengths. The site is cleared and the correct position of the foundation is being fixed. Then, excavation commences from the reduced level down to the desired level. A layer of lean concrete is being laid to prepare a clean and firm base for the footing. Formwork is then being built to allow concrete to be poured. Spacer blocks are placed before reinforcements being laid to provide sufficient concrete cover for rebars. After the rebar are being fixed into the formwork, stump reinforcements are then erected. Lastly, concrete will be poured and set. Curing shall be then performed. The ground beam construction will be started after the column stump has finished. Beam framework will be set accurately on the ground. Concrete is then laid out on ground surface into the framework. Reinforcements will be put with spacer block to protect the reinforcement from rust. For the ground floor, after the completion of ground beam, construction of cast in situ ground slab is constructed. First, formwork is being set, and then reinforced steel bars will be fixed on the positions. Finally, concrete will be poured into the framework. Curing is then performed. For the precast columns, after the in-situ foundation and ground floor slab has been constructed, the precast columns with a height of 3.3 meters is then being placed on the exact position of the RC stumps, where the columns will be locked down to the RC stumps using connection bolts. For the precast wall, there are different types of 3 meters height of precast wall panels are transported to the side to be positioned, installed and sandwiched between the columns. Non-string mortar are used to seal the gaps along the bottom edge of the inner side of the panels. As for the precast beam, after the installations of wall panels, precast concrete beams are positioned and installed on top of the precast columns and wall panels. There are 3 types of beams: L-shaped, T-shaped, and flat beam. Precast beam is being installed last so that the weight is borne by both columns and the wall panels in this case. Lastly, different sizes of precast slabs are being transported to site and positioned on the beams. The installation joints that are between the slabs and the ends of slabs should be filled with fine aggregate concrete. Prior to concreting of joints and anchor ties, the joints were made sure to have no rubbish. The procedures are then repeated up to the 3rd floor. Final precast slabs are installed partially in the building as ceiling to allow installations of water tank. After that, steel roof trusses are installed on the roof beam with steel bracing fixing trusses onto the precast beam to prevent displacement. Then, steel battens are fixed onto the steel trusses according to the length. Finally, rod wool is installed as insulation following with aluminium foil as heat resistant and fire resistant. Metal roof decking is then installed as final layer. The precast wall as example to explain calculation. The length and the area of the selected wall panel is obtained through the given design. Volume is then calculated by multiplying the thickness of the wall panel. The mass of the wall is attained by multiplying the volume of the wall with the density obtained by the supplier. Finally, the embodied energy is attained by multiplying the mass of the wall with the energy coefficient of the concrete, which is 1.7 mg/kg. All the findings are then multiplied to the number of floors and adding up together. Through the calculations, we can see that the steel roof trusses have the highest embodied energy value, which causes total embodied energy of building to become higher. In order to reduce the value, the galvanized steel roof truss is switched to hardwood timber roof truss, which only has an energy coefficient of mg/kg. With the substitution of the timber roof truss, the total embodied energy is vastly reduced.